In the summer of 1940, as Britain braced for invasion, a quiet experiment unfolded at RAF Hornchurch in Essex. 2 Supermarine Spitfires were prepared for flight. Identical aircraft in every visible way. Same airframe, same Rolls-Royce Merlin engine, same armament, even the same pilot, squadron leader Desmond Cook. Cook climbed into the first aircraft and opened the throttle. It needed 320 yards of runway to lift off, and more than 11 minutes to reach 20,000 feet. It finally topped out at a ceiling of 32,000 feet, standard performance for the RAF's frontline fighter. Then Cook took off again in the second Spitfire. This flight was different. Takeoff distance, 225 yards. Time to 20,000 feet, just 7 minutes 42 seconds. Maximum altitude, 39,000 feet. Nothing had changed, except for one thing. The second Spitfire had been equipped with a different propeller. The transformation was immediate and impossible to ignore. In a war where seconds could decide survival, this single engineering upgrade had unlocked performance previously thought unattainable. A breakthrough dismissed for years as impractical and overly complex had suddenly proven itself in the skies over Britain. 3 blades of machined aluminum that would soon reshape the balance of air power in World War II. The story behind this breakthrough began not in a cockpit, but in a test facility in Connecticut, 8 years earlier. In February 1932, Frank Walker Caldwell stood on the oil-stained floor of Hamilton Standard's research plant in East Hartford. At 43 years old, Caldwell was already regarded as one of America's most capable propeller engineers, practical, disciplined, and unmoved by popular opinion. Those who worked with him remembered the same constant image: wire-rimmed glasses, a clipboard in hand, and a quiet confidence rooted in mathematics rather than speculation. Behind him, bolted to a roaring test stand, a polished aluminum propeller spun with controlled violence. What made it extraordinary was not its appearance, but its function. It could automatically change the angle of its blades while in flight. To most engineers of the era, such a mechanism seemed unnecessarily complex and likely to fail. Caldwell disagreed. Just 3 days earlier, he had received an urgent request from Boeing's airfield in Seattle. Their new Model 247 airliner, widely celebrated as the future of commercial aviation, was stranded in Denver, unable to climb above the Rocky Mountains with its standard fixed-pitch propellers. If the problem was not solved immediately, major airline orders were at risk. Caldwell was asked whether his experimental design could help. He knew it could, but convincing the rest of the aviation world would be another matter. At the time, the idea of a variable pitch propeller was widely dismissed as unreliable. Engineers argued it would be too heavy, too complicated, and dangerously prone to failure. Even the U.S. Army Air Corps had officially declared Caldwell's approach mechanically unsound. Yet he pressed forward, an engineer determined not to win arguments, but to prove them irrelevant. Caldwell's opportunity, and his greatest risk, came from a crisis in American aviation. In 1933, Boeing introduced the Model 247, a sleek twin-engine transport aircraft that promised to revolutionize air travel. It was faster, stronger, and more aerodynamic than anything before it. Airlines hailed it as the future of commercial flight, but that future nearly collapsed over the Rocky Mountains. During test operations at Denver Municipal Airport, the aircraft revealed a critical flaw. Its fixed-pitch wooden propellers, designed for efficiency at cruising speed, robbed the engines of power during takeoff and climb. At high-altitude airfields like Denver, where thinner air already reduced engine output, the Model 247 struggled to clear terrain. It could barely gain altitude, making it unsafe and commercially useless. Panic spread quickly through the industry. Pan American Airways President Juan Trippe issued Boeing a blunt ultimatum: fix the problem or lose the contract. United Airlines had already committed to 25 aircraft, and other airlines were watching closely. If Boeing failed, Douglas Aircraft stood ready to seize the market with its own design. Caldwell had seen this problem before. Aviation had reached a performance wall. not because of engines or airframes, but because of a single overlooked component, the propeller. A fixed-pitch design worked well only at one specific airspeed or altitude. Everywhere else it was a compromise that wasted power. His variable pitch propeller was the solution, but few believed it. Critics across the aviation community repeated the same objections. The mechanism was too heavy, too fragile, too complex for real-world flying. Charles Lindbergh himself had privately questioned whether automatic propeller control was a theoretical advantage with no practical future. Yet Caldwell refused to yield. He trusted his data. Every wind tunnel test, every trial on the dynamometer told the same story. A propeller that could change its blade angle in flight would unlock massive gains in power and efficiency. All he needed was a chance to prove it in the air. That chance was about to arrive. On February 15, 1933, Caldwell finally received the opportunity he had been waiting for. United Airlines President Pat Patterson authorized a single test flight to determine whether Hamilton Standard's experimental propeller could rescue the Boeing 247 from commercial failure. It would be a decisive moment. Success meant survival. Failure would likely end the project permanently. Test pilot Eddie Allen, a calm and meticulous aviator known for his precision under pressure, was selected to conduct the flight. Mechanics installed Caldwell's prototype constant speed propeller onto one of Boeing's grounded aircraft in Denver. Alongside it, they fitted a compact hydraulic governor linked to the engine. Together, the system could automatically adjust blade pitch in response to airspeed and engine load, maintaining constant RPM and maximizing performance without pilot input. Allen advanced the throttles and lifted off toward the mountains that had halted every previous attempt. At 6,000 feet, the altitude where earlier flights had stalled, the modified aircraft continued climbing with ease. It passed 8,000 feet, then 10,000, still gaining altitude. The Rocky Mountains, once an immovable barrier, now seemed to fall beneath it. By the end of the test, the results were undeniable. The service ceiling had increased from 12,500 to over 20,000 feet. Cruise speed improved by 15 miles per hour. Fuel efficiency rose by 12%. For the first time, a commercial aircraft had achieved optimal engine performance at every stage of flight: takeoff, climb, and cruise. That evening, Patterson sent a telegram to Hamilton Standard headquarters in Connecticut. Its message was brief but historic. Constant speed propeller exceeds all performance claims. Recommend immediate adoption. Within weeks, orders flooded in from airlines across the United States. The impossible propeller had not only worked, it had changed aviation. But its greatest impact was still to come. War was approaching, and the world's air forces were about to discover just how powerful Caldwell's invention really was. The success of the Boeing 247 test flight did more than save a commercial airliner. It captured the attention of the U.S. military. Until then, Caldwell's design had been viewed as an experimental curiosity with limited relevance to combat aviation. But the dramatic climb performance of the modified 247 raised an important question within military engineering circles. If constant speed propellers could transform an airliner, what could they do for a fighter? The answer soon became a matter of national security. In May 1933, Caldwell received a call from Washington, D.C. The U.S. Navy wanted a meeting. Commander John Towers from the Bureau of Aeronautics explained their interest plainly. Aircraft were growing faster every year, but propeller technology had fallen behind. The next generation of fighters and bombers would need far better takeoff performance, higher climb rates, and greater range. Without a breakthrough in propulsion efficiency, engine power alone would not be enough. Caldwell knew exactly what they were looking for. He met with Navy officials and outlined the capabilities of his constant speed propeller system. In combat, he argued, automatic pitch control would allow a pilot to focus on maneuvering rather than engine management. The propeller would act like an automatic transmission, delivering maximum thrust during combat climbs and conserving fuel during long-range patrols. In multi-engine aircraft, the feathering system would allow crews to shut down a damaged engine without losing control. For the Navy and Army Air Corps, this was more than an incremental improvement. It was a tactical advantage. Within months, the first contracts were signed. Hamilton's Standard would adapt Caldwell's design for American military aircraft. What began as a solution for commercial aviation was now evolving into a weapon of war. The United States had not yet entered the growing conflict overseas, but its engineers were already preparing for a future in which air power would decide wars. And Frank Caldwell had just become a central figure in that future.
Recognition came quickly. On November 13, 1933, Frank Caldwell received news that his work had earned one of the highest honors in aviation. The National Aeronautic Association awarded Hamilton Standard the prestigious Collier Trophy for the development of the controllable pitch propeller, with special credit given to Caldwell for his engineering leadership. Only the most significant contributions to aeronautics received such recognition. Previous recipients included Charles Lindbergh, General Billy Mitchell, and the Wright brothers. In December, Caldwell traveled to the White House, where President Franklin D. Roosevelt personally congratulated him for advancing American aviation. It was a public triumph, the official validation of an idea that had been fiercely opposed for years. But while the photographs from the ceremony suggested victory, the reality inside the aviation industry was far more complicated. Resistance remained strong, especially within military ranks. At Wright Field in Ohio, the U.S. Army Air Corps' main testing ground, some pilots and engineers were openly skeptical of the new propellers. They questioned whether a hydraulic system full of moving parts could survive combat conditions. Major Benjamin Kelsey, one of the Air Corps' leading test pilots, voiced their concerns bluntly. "What happens when that system fails over enemy territory?" he asked. "Fixed-pitch propellers don't break because they have nothing to break." To many, simplicity meant survival, and Caldwell's design looked anything but simple. Oil lines, governors, pistons. One failure could leave a pilot stranded with a windmilling propeller and no way home. Even as American aircraft manufacturers placed new orders, doubt lingered. Caldwell understood that speeches and ceremonies would not win over skeptics. Only evidence would. If military leaders demanded proof that his propellers were reliable under real-world conditions, he would give it to them through data, testing, and engineering discipline. The next phase of his work would be the most demanding, proving not just performance, but absolute reliability. To silence the remaining opposition, Caldwell knew he had to do more than claim reliability. He had to prove it beyond question. At Hamilton Standard's expanding test facility in East Hartford, he led a rigorous program designed to push his propellers far past the limits of normal flight. The key to the system was the hydromatic propeller, Caldwell's most important mechanical achievement. It used engine oil, already available under pressure, to adjust the angle of each blade automatically during flight. A compact centrifugal governor maintained constant engine RPM by continuously altering blade pitch, allowing the engine to operate at peak efficiency in every condition. The design offered a series of critical advantages. Shorter takeoffs. At low air speeds, the blades shifted to a fine pitch, equivalent to low gear in a car, allowing the engine to accelerate quickly. Improved climb performance. As altitude increased, the governor adjusted blade pitch to maintain engine RPM, preserving power where fixed-pitch designs lost efficiency. Higher top speed. In level flight, the blades moved to a coarse pitch, reducing drag and increasing fuel-efficient cruise speed. Engine protection. During steep dives, the propeller automatically increased blade angle to prevent engine overspeed. Feathering capability. In multi-engine aircraft, a failed engine could be shut down safely by rotating its propeller parallel to the airflow, dramatically reducing drag. On paper, it was a masterpiece of precision engineering, simple in function, yet mechanically sophisticated. Still, critics argued that the hydromatic propeller would never withstand harsh operational use. To answer them, Caldwell introduced a testing method that would become legendary inside the industry, the World Test. Propellers were mounted on heavy stands and driven at full power for hundreds of hours. Engineers measured thrust, vibration, stress loads, and mechanical fatigue. They ran engines at extreme RPM levels and subjected components to violent oscillations to expose any point of weakness. If a part failed, it was redesigned. If it survived, the test became more demanding. The philosophy was clear. No failure in combat should ever come from a lack of preparation and testing. By the end of 1934, Caldwell was no longer just improving propellers. He was redefining aviation reliability standards. Despite the growing body of test data, some American aircraft manufacturers and military officers still resisted the adoption of constant-speed propellers. Many believed traditional fixed-pitch designs were good enough and were reluctant to retool factories or retrain mechanics for a system they considered unproven. Caldwell realized that laboratory tests alone would not settle the debate. Pilots needed to see the difference with their own eyes. That opportunity came on March 21, 1934, at Selfridge Field in Michigan. A simple but decisive demonstration was arranged involving two identical Curtiss P-26 fighters. The only difference between them was the propeller. One used the standard fixed-pitch unit, while the other was equipped with Caldwell's constant-speed system. The aircraft took off simultaneously and began a timed climb. The results were immediate and dramatic. The fixed-pitch fighter reached 10,000 feet in 8 minutes and 30 seconds. The constant-speed version arrived nearly 3 minutes faster, in 5 minutes and 40 seconds. At 15,000 feet, the advantage widened even further. Top speed increased from 187 to 203 miles per hour, and the service ceiling rose from 28,000 to 34,500 feet. Pilots and officials who had come expecting to witness a marginal improvement instead saw a transformation in performance. Lieutenant Colonel Carl Toohey Spatz, who would later command U.S. strategic air forces in Europe, filed an urgent report after the test. The performance advantage is so significant that it represents a fundamental shift in combat capability. One demonstration had done what months of technical reports could not. The U.S. Army, Air Corps, and Navy began ordering Hamilton standard propellers for fighters and bombers alike. Aircraft that struggled at high altitude were suddenly capable of climbing faster, flying higher, and reaching combat areas sooner. For Frank Caldwell, the message was clear. The constant-speed propeller was no longer an experimental idea. It was now a strategic necessity. And as war clouds gathered over Europe and Asia, that necessity would soon become urgent. While the United States advanced rapidly in propeller technology, Europe lagged behind. By the late 1930s, war in Europe was no longer a possibility. It was imminent. Yet the major air forces of Britain and Germany were preparing to fight it with outdated propeller systems. In Germany, the Luftwaffe's new frontline fighter, the Messerschmitt Bf 109, entered service with a manually adjustable propeller. Pilots had to constantly adjust blade pitch using a hand lever inside the cockpit. In combat, where split-second decisions meant survival, this system forced pilots to divide their focus between flying and engine control. Britain faced similar limitations. Early models of the Supermarine Spitfire and Hawker Hurricane were still using two-position propellers. These systems allowed only two settings: fine pitch for takeoff and coarse pitch for cruising. There was no automatic adjustment, no ability to optimize climbing performance, and no response to rapidly changing combat conditions. The consequences became apparent as soon as the war began. In September 1939, Royal Air Force pilots fighting over Europe reported a disturbing trend. German fighters were gaining altitude faster and holding the advantage in vertical maneuvering. Above 15,000 feet, RAF fighters struggled to maintain power, while Luftwaffe pilots adjusted their propellers manually to match changing air conditions. Air Ministry reports warned that British fighter performance was critically limited at operational altitudes. Bomber crews found themselves abandoning missions because their aircraft could not climb high enough to cross the Alps. Fighter squadrons lost intercept opportunities simply because they couldn't reach enemy aircraft in time. The gap was not a matter of pilot skill or aircraft design. The Spitfire was one of the finest fighters ever built. The issue was mechanical. The engines were losing battles that the airframe should have won. Frank Caldwell's automatic propeller could have solved that problem, but Britain had not yet adopted it. That would change, but only because one squadron leader refused to accept defeat.
By mid-1940, Britain stood alone against Nazi Germany. With France defeated and the Luftwaffe preparing for a full assault across the English Channel, air superiority was no longer a strategic goal. It was a matter of survival. Inside RAF Fighter Command, the numbers were alarming. Intelligence reports showed that German fighter units were climbing faster. reaching higher altitudes, and controlling the terms of engagement. The RAF still relied heavily on two-position propellers, limiting the full power of the Rolls-Royce Merlin engines that powered both the Spitfire and the Hurricane. Air Chief Marshal Hugh Dowding, head of Fighter Command, recognized that Britain faced not just a numerical disadvantage, but a technological one. German aircraft could choose when to engage and when to escape. RAF squadrons often arrived too late to intercept bomber formations or were forced to break off combat when they could no longer maintain altitude. The situation was summarized bluntly in a classified Air Ministry report from June 1940. Current propeller technology imposes severe altitude limitations, reducing interception capability and combat effectiveness. One of the pilots feeling this disadvantage most sharply was Squadron Leader Desmond Cook of No. 65 Squadron. He had seen the problem firsthand over France and during the evacuation at Dunkirk. In engagements above 15,000 feet, Messerschmitt Bf-10-9s routinely outclimbed British fighters, gaining the upper hand before combat even began. It wasn't a question of courage. The RAF pilots were outperformed by machinery. Cook knew that the solution existed. He had studied performance reports from the United States and understood what a constant-speed propeller could do. But bureaucracy inside the Air Ministry had delayed its adoption. Committees debated costs and logistics while Luftwaffe squadrons gathered across the Channel. Cook decided he would not wait for permission. On June 10, 1940, with invasion threatening and RAF losses mounting, Squadron Leader Desmond Cook took matters into his own hands. Stationed at RAF Hornchurch in Essex, Cook understood that his Spitfires were being outperformed not because of poor design, but because of outdated equipment. The solution, he believed, was already proven in America: the constant-speed propeller. Rather than waiting for official approval, a process that could take months, Cook acted on his own initiative. He bypassed the chain of command and placed a direct call to de Havilland Propellers, which held the British production license for Hamilton Standard's design. His request was urgent and uncompromising: convert my squadron's Spitfires immediately. Within 48 hours, a small team of de Havilland engineers arrived at Hornchurch under special authorization. The work began in secrecy to avoid bureaucratic interference. Each conversion required roughly 8 hours of precision labor. The old two-position propellers were removed, hydraulic systems were installed, governors calibrated, and the new constant-speed propellers mounted. Ground crews worked in rotation to keep aircraft available for combat while modifications were completed. The first converted aircraft, Spitfire, Mark I, serial number K9847, was ready by June 15, 1940. Cook conducted the maiden test flight himself. The difference was immediately clear. On takeoff, the engine reached full power without strain as the propeller automatically adjusted to fine pitch. The aircraft lifted off the ground after just 225 yards, nearly 100 yards less than before. Then came the climb test. Cook opened the throttle and began a continuous ascent toward 20,000 feet, the expected altitude of incoming German bomber formations. The Spitfire climbed with a level of performance he had never experienced. The engine maintained optimal RPM throughout the climb without requiring manual propeller input. Time to 20,000 feet, 7 minutes, 42 seconds. Nearly 4 minutes faster than before. Cook didn't stop. He continued climbing, past 30,000 feet, then 35,000, then 37,000. Finally, at 39,000 feet, he reached the aircraft's new service ceiling, an altitude no RAF Spitfire had achieved before. He landed, taxied to a stop, climbed from the cockpit, and made a single phone call to Fighter Command Headquarters. His message was simple: the Spitfire is now an airplane. Conversion of his entire squadron began immediately. Following Cook's bold initiative, Fighter Command moved with unprecedented urgency. Within 72 hours, all 12 operational Spitfires of No. 65 Squadron had been converted to constant-speed propellers. News of the transformation spread quickly across the RAF. What had begun as an unofficial modification now became a national priority. By late June 1940, de Havilland engineers were working around the clock, converting Spitfires and Hurricanes at airfields across southern England. Aircraft were pulled from frontline service for less than 24 hours at a time to avoid weakening home defense during the expected invasion. Mechanics learned to install the new systems in record time. By September 1940, just as the Battle of Britain reached its climax, 90% of RAF fighters were equipped with constant-speed propellers. The effect on combat performance was immediate and measurable. Performance. Factor before, 2-position prop. After, constant speed. Time to 20,000 feet, 11 minutes, 8 seconds, 7 minutes, 42-second service. Ceiling 32,000 feet, 39,000 feet. Takeoff distance 320 yards. 225 yards patrol time limited, plus 45-minute endurance pilot reactions captured the significance of the change. Flight Lieutenant Brian Lane of 65 Squadron wrote in his combat diary, "It's as if someone has replaced our engines with twice the power. We can climb with the 109s now." Tactically, the RAF now held the advantage of altitude, one of the most decisive factors in air combat. Spitfires and Hurricanes could reach interception height 2 to 3 minutes faster than German planners expected. In high-altitude engagements, British fighters now attacked from above, using gravity and energy to dictate the fight. Exactly the strategy Dowding had envisioned for fighter command. The new propellers also reduced pilot workload. Instead of manually managing propeller pitch during combat, RAF pilots could now focus entirely on maneuvering and fire control. Meanwhile, Luftwaffe pilots continued flying aircraft that still required manual propeller adjustments, forcing them to divide attention during dogfights. Frank Caldwell's invention had crossed the Atlantic just in time. The RAF entered the Battle of Britain outnumbered, but no longer outperformed. While the constant-speed propeller helped secure British skies in 1940, its greatest test was still to come. When the United States entered the war after the attack on Pearl Harbor, America launched a massive industrial mobilization. Air power would be central to that effort, and Frank Caldwell's propeller would become one of its most vital components. By 1942, nearly every major American combat aircraft relied on Hamilton's standard propellers. The list included icons of the air war: B-17 Flying Fortress, B-24 Liberator, P-51 Mustang, P-47 Thunderbolt, P-38. Lightning without constant-speed propellers, these aircraft could not have achieved the climb rates, fuel efficiency, or combat range that made them effective. But as demand surged, so did production pressure. Hamilton Standard expanded from a modest engineering firm into a vast war industry. The East Hartford plant grew into a network of factories linked to subcontractors across the United States. Within a decade, the company had gone from 800 workers to 22,000 employees, operating 3 shifts a day, 7 days a week. Automobile manufacturers like Nash Kelvinator, appliance builders like Frigidaire, and industrial firms like Remington Rand were recruited to join production. Assembly lines once used to build refrigerators, typewriters, and car engines were retooled to manufacture precision propeller components. By mid-war, 530,000 propeller assemblies were on order. Production peaked at 12,000 complete propellers per month. Each propeller required 47 precision machine parts with microscopic tolerances. But mass production brought new challenges. Unlike other aircraft components, propellers operated under violent loads at high speed. A single manufacturing defect could be catastrophic in flight. By late 1942, internal reports revealed a troubling trend. Propeller failure rates were increasing. The rush to meet military demand had stretched the quality control process to its limits. Some newly trained factory workers lacked experience, and subassembly errors began slipping through inspection lines. The consequences of these failures would soon be felt in deadly fashion over Germany. The industrial surge that made Allied air power possible also introduced dangerous new risks. As production accelerated, small defects began to slip through the system. Defects that would have serious consequences in combat. The most alarming incident occurred on October 14, 1943, during the Second American bombing raid on Schweinfurt, Germany, a mission later known as Black Thursday because of the heavy aircraft losses. Over enemy territory, a B-17 Flying Fortress named Hell's Angels took a direct hit from anti-aircraft fire that crippled its No. 3 engine. The crew shut the engine down and engaged the feathering system, designed to rotate the propeller parallel to the airflow and eliminate drag. At first, it worked, but minutes later, something went wrong. The propeller slowly rotated back into the airstream, a condition known as unfeathering, and began windmilling violently. The drag was so severe that the bomber could no longer hold altitude. The aircraft rolled, stalled, and crashed into a forest below. 9 crew members were killed. An investigation traced the failure to a batch of hydraulic governors contaminated during manufacturing. Water and microscopic debris inside the oil system had frozen at high altitude, blocking pressure flow to the propeller piston. When engineers inspected propellers from the same production run, they found 47 more units with identical contamination, already installed on aircraft across the 8th Air Force in England. For Frank Caldwell, now 54 years old, this was not a distant engineering failure. It was a personal one. He flew to Britain to meet with air crews and listen directly to frontline mechanics who had struggled with propeller issues in freezing, combat-damaged conditions. One flight engineer from a B-24 squadron told him bluntly, "Your propellers work in training, but over Germany, with flak damage and frozen oil, they fail when we need them most." Caldwell returned to Connecticut and immediately began a full redesign of the feathering system. New safeguards were introduced: redundant hydraulic circuits to prevent total pressure loss, mechanical locks to hold feathered blades in place even without oil pressure, contamination-resistant seals to prevent ice formation, emergency manual control if automatic systems failed. Quality control was overhauled. Every propeller now had to survive, temperature cycling from -60 degrees Fahrenheit to +140 degrees Fahrenheit, vibration tests exceeding combat stress by 75%, contaminated oil trials with metal fragments and ice crystals, runaway propeller simulations to test structural integrity. By 1944, failure rates dropped to less than 1% of all mechanical issues in U.S. Army Air Force's records. The constant speed system, once criticized as too complex for war, became one of the most trusted systems in Allied aviation, and soon its true strategic impact would be revealed over Europe and the Pacific. By 1944, the constant speed propeller was no longer an experimental innovation or a controversial upgrade. It was a decisive factor in Allied air superiority. Its impact could be measured in combat victories, aircraft range, climb rates, and survival statistics. On the eastern and western fronts, dogfights were won not only by pilot skill, but by engineering. In identical aircraft, altitude and energy decided the fight, and Frank Caldwell's invention delivered both. European theater. When the P-51 Mustang entered long-range escort service over Europe, it transformed the air war. With Hamilton standard constant-speed propellers, the Mustang gained 40% faster climb rates than fixed-pitch equivalents, a 30 miles per hour speed advantage over the latest Bf-10-9K models, 5,000 feet higher service ceiling than German interceptors, 2,000-mile range with drop tanks, enabling full escort to Berlin. For the first time, American bombers had fighter protection from takeoff to target and back again. Luftwaffe pilots, who once attacked from above with energy dominance, now found themselves outclimbed and outmaneuvered by Allied fighters. The constant-speed propeller also saved lives. In multi-engine bombers like the B-17 Flying Fortress and B-24 Liberator, engines frequently took damage from flak or enemy fire. Without feathering capability, a single dead engine could pull an aircraft into a fatal spin. But with Caldwell's system, thousands of bombers continued flying after engine loss, crews returned safely from missions once considered hopeless, aircraft survivability increased dramatically on long-range missions. Pacific theater. In the Pacific, the propeller proved equally vital. Early in the war, Japanese A-6M0 fighters dominated with agility and climb performance. But new American fighters like the P-47 Thunderbolt and F-6F Hellcat turned the tide. With constant speed propellers, these heavier American aircraft could, maintain full engine power during rapid altitude changes, climb 40% faster than Japanese aircraft at combat altitudes, outdive enemy fighters without engine overspeed, chase and intercept targets once considered untouchable. The results were clear. By mid-1944, the Hellcat achieved a 19-to-1 kill ratio in the Pacific, an outcome made possible by overwhelming performance advantages. In a confidential memo to the Pentagon, General Carl Toohey Spaatz, commander of U.S. strategic air forces in Europe, wrote, "The constant speed propeller has given American aircraft decisive performance advantages in every theater of war. The propeller that many engineers once dismissed as too complex had become one of the most important technologies of World War II. By the end of World War II, the constant speed propeller had reshaped global aviation. What began as an experiment in a small Connecticut test bay became one of the most important engineering breakthroughs of the war. It gave aircraft the ability to climb faster, fly higher, and travel farther than ever before. Advantages that saved lives and changed the course of battles. A post-war analysis by the U.S. Army Air Forces revealed extraordinary statistics. Improved climb performance prevented an estimated 5,000 fighter losses. Higher service ceilings saved approximately 3,000 aircraft that would have otherwise been intercepted. Propeller feathering allowed more than 6,000 bombers to return home after engine damage. Fuel efficiency gains reduced forced landings and emergency ditchings by over 1,000 aircraft. In total, engineers estimated that the constant speed propeller directly prevented over 15,000 Allied aircraft losses during the war. Frank W. Caldwell, once dismissed as a dreamer promoting an impractical design, had proven his critics wrong. The invention that many said was too complex for combat became one of the most reliable systems in military aviation. His hydromatic propeller powered the aircraft that defended Britain, liberated Europe, and turned the air war in the Pacific. Today, Caldwell's achievement remains a defining example of engineering persistence, of a man who trusted data over doubt and proved that innovation often begins where certainty ends. Long before the jet age began, he helped push aviation into a new era of performance. And in doing so, he changed the outcome of history, 3 blades at a time.